All right. Hello, everybody. Welcome to the Atmospheric Theoretical to Applied Science session, part one. My name is Kyle Ziolkowski. I'm the session host for this. So we have, it looks like a list of great talks coming up here this morning. But first I want to take this time to do a land acknowledgement. So I would like to take a moment to acknowledge the land of the Indigenous peoples of all lands, coast to coast, that we are on today. We acknowledge the ancestral and unceded territory of all Inuit, Métis, and First Nations people that call this land home. So just so we'll start off, I guess. Annie, I guess you can share your screen. I'll stop sharing, and Annie, you can start your presentation. Speakers will have roughly about 10 minutes to 12 minutes, sorry, to present. And I also ask that if you have any questions, I encourage questions to put them in the Q&A, and we can, and at the end of the session, we will go over questions. So Annie, if you don't mind introducing yourself, and you can get started.
Hi, my name is Annie Duhamel. I will do my presentation in French, but all my slides are in English. Je travaille à la... Sorry. Je travaille dans l'équipe de réponse aux enjeux en qualité de l'air Environnement Canada. Et aujourd'hui, je vais vous parler d'une étude qualitative de la réponse aux enjeux d'un modèle de qualité de l'air dans le cadre de la réduction linéaire de la pollution anthropogénique canadienne. Je vais vous présenter mon équipe, vous parler du but de cette étude-là, les bases de l'expérience, quelques résultats et je vais conclure. Donc, notre équipe travaille principalement à des réglementations canadiennes en matière de qualité de l'air ambiant. Nos partenaires principaux sont Santé Canada pour les impacts sur la santé et la division des politiques stratégiques pour les impacts sur l'environnement comme la visibilité. Nous travaillons aussi avec certaines universités. Donc, le but de cette étude est d'apprendre comment le modèle de qualité de l'air canadien, GEMMAC, répond à un changement linéaire des émissions anthropogéniques données en entrée au modèle. En premier lieu, on utilise les inventaires d'émissions qui sont fournis par différents pays. Puis, ce sont des totaux annuels qu'on met dans un logiciel qui s'appelle Smoke. Et ce logiciel-là permet d'allouer spatialement et temporellement, ainsi que de faire la spéciation chimique de certains groupes, comme les composants, les PM2.5 et les composés volatiles organiques, les VOC. On ne met pas de feux de forêt dans nos simulations. On utilise des émissions biogéniques reliées à l'année de météorologie qu'on utilise. Puis, on utilise le modèle GEMMAC opérationnel canadien pour piloter le modèle au niveau des variables météorologiques. Ensuite, on roule GEMMAC sur une période d'une année avec un certain set d'émissions. Puis, on fait du post-traitement qui sont généralement des moyennes, trouver des maximums de moyennes, des différences avec d'autres simulations qu'on a fait qui sont comparables. Donc, pour cette expérience-là, nous avons utilisé les émissions anthropogéniques du Canada de 2015, provenant de l'APEI de 2017. Pour les États-Unis, on a utilisé les émissions valides en 2016 de Equates, puis on a utilisé les émissions du Mexique de 2008. On a utilisé l'année de météorologie 2019. Le domaine de résolution va de l'océan Pacifique à l'océan Atlantique et du Mexique jusqu'au nord du Canada, à une résolution de 10 km et utilise environ 84 niveaux verticaux. Nous avons fait 6 simulations d'une année en changeant uniquement les émissions anthropogéniques canadiennes. Donc, on a fait un code base où on ne change rien et ensuite, on a réduit pour chacun des points de grille du domaine reliés aux émissions canadiennes 20 des émissions. Donc, à toutes les fois, on a fait 20 40, 60, 80 et 100 des émissions. Donc, je vais vous présenter les résultats en utilisant les polluants qu'on utilise pour calculer la cote air santé, l'AQHI, soit le dioxyde d'azote, les particules fines de 2,5 microns et moins, et l'ozone troposphérique, c'est-à-dire celle qui est proche de la surface. La moyenne annuelle du NO2 ressemble un peu à cette image, qui est donc, on peut voir que dans les villes, le maximum va jusqu'à 35 microgrammes par mètre cube. On peut voir les routes et les génératrices dans le nord. Maintenant, si on réduit progressivement, on peut voir que l'impact est de plus en plus grand dans les villes parce que c'est les zones où il y a le plus d'émissions de NO2. Et puis, on voit aussi les voies maritimes apparaître. Donc, au maximum, les différences, l'impact canadien est de 20 microgrammes, 20 ppbv. Dans la simulation où on n'a plus d'émissions canadiennes anthropogéniques, il ne reste que les émissions biogéniques et les émissions anthropogéniques des États-Unis et du Mexique. J'ai fait une analyse sur les villes. Donc, les concentrations sont sur l'axe TY et les réductions sont sur l'axe TX. Donc, ici, on a le cas de base et ici, on a le cas où on n'a plus du tout d'émissions canadiennes. Les courbes oranges représentent les villes, les métropoles, et les bleus comme les grandes villes. Les deux plus hautes sont Calgary et Edmonton. Les courbes grises sont des villes où la quantité de population est de moins de 500 000 habitants. Je vais en parler un peu plus tard. On peut observer que la variation de concentration ne semble pas suivre une courbe linéaire lorsque les concentrations de base dépassent un certain seuil. Pour le groupe de 100 000 à 500 000 habitants, on peut voir que les réactions est relativement similaires, à l'exception de Windsor, où on peut voir que les émissions anthropogéniques des États-Unis ont un plus grand impact dans la zone des Trois-Windsor que dans le sud de la Colombie-Britannique, où on voit qu'à Vancouver, il y a presque plus de concentration de NO2. Ensuite, pour les villes de 50 000 à 100 000 habitants, la réaction est similaire au groupe précédent. Pour les villes de moins de 1000 habitants et entre 1000 et 50 000 habitants, les concentrations semblent plutôt corrélées avec certaines des industries qu'avec la population, puisque Fort McMurray a très peu d'habitants et pourtant sa concentration est aussi élevée que certaines villes avec plus de 50 000 habitants. Maintenant, avec les PM 2,5, la concentration ressemble à ceci. Fort McMurray est ici. Donc, les émissions canadiennes maximum sont de... Non. La concentration moyenne annuelle des PM 2,5 est de 32 microgrammes par mètre cube. Si on réduit les concentrations régulièrement, on peut voir la même réaction que pour l'NO2, où les concentrations se creusent dans les villes et on peut voir même les voies maritimes apparaître. L'impact maximal est de 32 microgrammes par mètre cube. Si on regarde dans les villes, pour le graphique des métropoles et des grandes villes, la variation des concentrations entre le code base et plus d'émissions canadiennes est relativement linéaire. La réponse est très similaire au niveau des villes de 100 000 à 500 000 habitants à propos des effets transfrontaliers. Et même un peu plus élevé, probablement causé par le fait que les PM 2,5 se promènent plus que les NO2. Maintenant, pour les villes plus petites, la concentration varie linéairement de la même façon. Maintenant, pour l'ozone, la concentration de base, on utilise une métrique différente qui est la moyenne annuelle des maximums journaliers. La concentration de base est de 26 ppbv. Et lorsqu'on réduit les émissions canadiennes, il y a une augmentation de l'ozone dans les villes et une réduction partout autour. C'est causé par la titration de l'ozone. Lorsqu'on réduit le NO, il y a plus d'O3 qui peut se produire, ou en fait qui n'est pas détruit par l'augmentation du NO. L'impact maximal est absolu est de 6 microgrammes, 6 ppbv. Maintenant, pour la réponse de l'ozone, la corrélation est complètement non linéaire. Avec la réduction des émissions, la concentration d'ozone augmente généralement dans les grandes villes comme Vancouver et Edmonton. Les concentrations d'ozone réduisent loin des centres, comme Fort McMurray, et la réponse des petites villes est très variable. En conclusion, la concentration de NO2 semble aussi corrélée linéairement aux réductions des émissions jusqu'à un certain niveau. La concentration de NO2 est corrélée linéairement à la réduction des émissions. La réponse de concentration d'ozone est généralement non linéaire. Dans le sud-ouest de l'Ontario, les variations de concentration sont impactées par les émissions anthropogéniques transfrontalières et l'étude se poursuit avec Craig Strout de l'équipe de recherche de qualité de l'air d'Environnement et Changement climatique Canada, en collaboration avec mon équipe RECA, dans le but d'approfondir l'enquête sur les mécanismes impliqués. Merci.
Excellent. Thank you, Annie. I don't see any questions, but is there any questions from any of our speakers here? Oh, I got one question that came in here. A clarifying question. Did you reduce the emissions of all species together or separately in these simulations?
We reduce every species at the same level for every simulation. So for the simulation of 20%, we reduce it by 20% for every cells and every sectors of the domain.
Okay, thank you. Any other questions? Okay, well, I think we're good. So we'll move on. Our next talk, so let me double check, make sure I get it right, is from Lawson.
Hello, just 1 second to get it up here.
Yep.
Okay. Hello, everyone. My name is Lawson Gillespie, and I'm a PhD student working for Professor Deborah Wunsch at the University of Toronto and Dr. Felix Vogel as a student research affiliate at the Downsview Laboratory for Environment and Climate Change Canada. And today I would like to talk to you briefly about my work in measuring methane emissions from the waste sector in Southern Ontario. And here on this title slide, you can see an example of two of our mobile measurement platforms where we use precision greenhouse gas in situ analyzers combined with GPS-enabled weather stations in order to build up maps of concentrations across our survey domains. So first, a quick motivation. Methane, if you're not aware, is the second largest contributor to anthropogenic global warming. And it has been increasing sort of monotonically in the atmosphere since we started taking these high precision fiducial background measurements. So we've got in the top right corner here, the trend from the ALERT laboratory in Nunavut. And we can sort of see the alarming increase in methane, especially since the year 2010. It's an important gas for greenhouse gas for emissions reductions efforts because methane only has a a half-life in the atmosphere of about a decade. So if we were to reduce anthropogenic methane emissions today, we would expect to see sort of a temperature response in the atmosphere within our lifetime, which is not necessarily the case for CO2. So as far as emissions reduction potential goes, it is the low-hanging fruit available to us. So we have surveyed tens of thousands of kilometers with our atmospheric composition surveys across Southwestern Ontario, in particular targeting a number of these large active and closed landfill sites, as they are the plurality source of emissions in this region. In particular, in the Greater Toronto Area, we've done sort of extensive surveys, especially within the city of Toronto, and further out to measure some of these mostly closed landfills, in addition to water resource recovery facilities, otherwise known as wastewater treatment plants, and a couple of organic solid waste processing facilities. Overall, we've measured over 650 downwind transects from these facilities and estimated emissions from them. An introduction to inventories briefly. So in this talk, I'll talk about EDGAR, which is the emissions database for global atmospheric research. For my work, it's not very good because it does not allocate landfill emissions to particular facilities, but instead scales them by population distribution. So I'll just talk about it briefly later. There is the Scarpelli et al. 2018 inventory, which is an emissions inventory for anthropogenic methane emissions in Canada. It does allocate waste emissions to particular facilities scaled by population density. At Environment and Climate Change Canada, we have the Greenhouse Gas Reporting Program, GHGRP, which is facility self-reported emissions. As well, at Environment and Climate Change Canada, there's the Waste Reduction and Management Division. They employ 2 first-order decay models to estimate emissions from large landfills. The Pollutant Inventories and Reporting Division has an internal 1 by 1 kilometer high-resolution spatial methane inventory, which is not yet available to the public, which does also allocate emissions to particular facilities, although the number of facilities available are poor in that inventory. And as well, at the University of Toronto, we've developed the FLAME GTA inventory, which is the facility level and area methane emissions inventory for the Greater Toronto Area. And this is our highest resolution facility level emissions inventory available to us. Unfortunately, it's only within the Greater Toronto Area. So across the country, the majority of our anthropogenic methane emissions come from the oil and gas sector, but those are largely found in Alberta and Saskatchewan. So not necessarily of concern for my domain of study. The next largest source nationally is enteric fermentation. So this is the belching cows problem. And then the third largest source would be solid waste disposal. But zooming into the Greater Toronto Area, and I apologize for switching colors on you here, solid waste, according to our FLAME GTA inventory, makes up the vast majority of emissions, more than 2/3, less than 3/4, within the city. And if we were to look at the particular large facilities in the inventory, we see that the plurality of emissions can be allocated to just one site. It's this Keel Valley landfill, which was closed in 2008. At the time, it was the largest landfill in the country. And the majority can be allocated to 2 facilities, Keel Valley and Britannia, which are 2 of the largest landfills in the GTA. So this is just important to tuck away in the back of our minds as we look at what we actually measured in the atmosphere later. So how do we go from these sort of in situ mobile measurements to of concentrations in the atmosphere to emissions? First of all, we conduct our mobile surveys on public roads, ideally on transect paths which are perpendicular to wind direction and downwind more than 100 meters, less than 3 or 4 kilometers from sources, depending on how much they emit to the atmosphere. So here we can see an example of 6 repeated transects downwind of a compost facility in the eastern GTA on January 6th, 2023. And we can see that the background concentration of methane shown here in red is relatively stable. And when we're downwind of this facility, we see large enhancements relative to this background concentration. And then what we do with these is we do a relatively rudimentary inverse analysis by fitting a very simple Gaussian plume dispersion model to these data. In particular, what we do is we fit the enhancement or the area under this enhancement curve, and try and match that to our observations by changing the emissions rate from the facility as modeled. And this gives us our posterior estimate of what the emissions would be from this facility. An important result from our study is that the transect to transect variability from these measurements often exceeds the other sources of uncertainty, in particular the source location uncertainty within a given facility. So we develop sort of reliable and robust statistics by repeating many downwind transects. And if there's changes to the facility's emissions over any given time period, we try and conduct more measurements across the calendar year. And so we've done this, these repeated measurements for a number of facilities, and at some other facilities we don't have as robust of a data set, but I'll present all of them for you here now. So for our water resource recovery facilities that we've surveyed, I have for you on the y-axis here an upscaled annual emissions total. So if we were to take any given downwind transect and upscale what our emissions estimate for that transect was to an annual total, that would be given in the distribution, the violin plots in black. And then our various inventories are represented as bar charts next to them. So the Flame GTA inventory in blue and the Scarpelli inventory in green here. Largely, we can see that the Flame GTA inventory is doing okay for our two largest facilities as predicted by this inventory, but seems to underestimate for the rest of the facilities in the Greater Toronto Area. And the Scarpelli inventory is a bit all over the place with respect to the wastewater recovery facilities. A convincing result for us was that the amount of methane emissions that we observed from these facilities did tend to scale very linearly with the amount of wastewater treated at each site, which is a good sign, at least for our measurement methodology. We also measured at some compost facilities, and I'll just have you pay attention. The scale on this y-axis is going to jump around a bit as well. And a key takeaway for us is that when we went to go measure these closed landfills in the Greater Toronto Area, we found significantly smaller emissions than the inventories predicted, drastically so for the Keel Valley landfill, which is the first one shown on the left here. So if we were to go from a bottom-up accounting in our inventory of what the emissions were in the Flame GTA inventory to a measurement-based methodology, we would subtract about a third of Toronto's methane emissions just from this single facility. So this exercise was really eye-opening and important, and contradicts a number of recent studies from satellite measurements of Toronto. So that big picture look, we know that there's lots of methane emissions in Toronto, but they are not from the facilities where we would expect them to be based on our ground-based surveys. So just highlighting again the Keel Valley and Britannia landfills, both of which have much smaller emissions than were first predicted. As well, the y-axis again has jumped here for these large active facilities in Southern Ontario. These active landfills, they have working faces where methane just seeps out the side, and we see significantly greater emissions from these sites than we do within the Greater Toronto Area, which was not necessarily predicted in various inventories. You can ask me questions about why that is later. Lastly, I've had to grapple with some problems with how to report sort of these asymmetric distributions as annual totals. So here I've got some normalized histograms of our measurements of methane emissions, all scaled to the fraction of the mean measured emissions for each facility to develop a sufficiently robust data set to show these distributions. The key takeaway for me is that wastewater treatment plants are pretty Gaussian-ish, but landfills are not very Gaussian at all. And so just showing you some quantile plots of best distribution fits to these. For the landfills, considering all of the data here in blue, for a Gaussian distribution, we see that it's not a great fit on the quantile plot, nor is it a great fit for a log normal distribution. Whereas for wastewater treatment plants here, I've got in blue a Gaussian distribution on a quantile plot, and orange is the log normal distribution. It does appear to be more Gaussian, which might mean that just a standard mean and standard deviation might be an appropriate estimate of the emissions and uncertainty from this methodology for those. But for landfills, we're resorting to using a median and quartile ranges to report emissions currently. Lastly, we have some interesting trends in landfill emission rates. So we see that they tend to scale with synoptic scale pressure tendencies. So as the pressure drops, landfill emissions tend to increase as well.
2
They
minutes.
tend to peak towards 0 degrees Celsius. And the combined effect of these gives us a sort of observable seasonal cycle in methane emissions from landfills that peaks in the wintertime. And you can ask me why later. So in summary, we've done over 650 downwind transects to quantify emissions from 39 facilities. Solid waste emissions from large landfills are significantly overestimated in our inventories for the Greater Toronto Area. In particular, Keel Valley Landfill is not the second largest source of methane emissions in Canada, as some inventories would suggest. Wastewater emissions seem to correlate strongly with the total volume of wastewater treated, and the factors influencing landfill methane emissions, some of them at least, are meteorological in nature. And thank you for your time and attention, and I would welcome any questions or insights or critiques of this work at this time. And work moving forward, as I've sort of hinted to here, we'll be looking at other species as well from these facilities. So we've got N2O in green there. Thank you.
Excellent, thank you. I don't see any questions in the chat. Do we have any from our speakers currently? No, okay. I have a question for you, Lawson. Just I'm a meteorologist and operational forecaster, so I'm kind of out of the realm of this type of work, but I'm just wondering, like, would you expect, I guess, because you're driving transects, and I think you're like, you have instrumentation on top of a car, correctly? Is that correct? Or is it?
So we have air intakes on the top of the car, and it sucks air into an analyzer, which is, you know, in the passenger seat.
Okay.
The back seat.
Gotcha. Okay. And so is like, I guess what I'm wondering is, like, we expect methane concentrations, I guess, would be high and nearest to the ground, and then they'll mix out as they kind of, you know, float away, right?
Yeah, we make some assumptions about the vertical and horizontal mixing from a Gaussian plume model. But since for landfills, a lot of these emissions are coming straight out of the ground, and at wastewater treatment plants, they're coming from sources which are not elevated, we do expect to find high concentrations at ground level, and that is indeed what we do see. Of course, it would be better to have more data. I'd love to have some sort of instrumentation that was a mobile tower, but that's impractical at the moment to implement.
Yeah, and do you see like a relationship with temperature? Like on a warmer day, there'd be more emissions?
That would depend on the particular source. For a landfill, the biology which drives the destruction of the methane in the cover soils is temperature dependent, and as well as the biology that produces the methane in the first place inside the landfill. The takeaway for me is that the temperatures inside the landfill are relatively constant, but the temperatures at the surface are driven by air temperature changes. So when it's cold, the methanotrophs, the microbes that eat the methane emissions, are inhibited relative to the ones inside the nice, warm, cooking, rotting mess inside of the landfill. So we actually see increases in emissions as the temperatures go towards 0 degrees Celsius, and fewer emissions from landfills on warm days.
Right. Okay, interesting. I'm learning lots anyways. All right, thank you, Lawson. We'll move on to our next talk, which, let me make sure I pull up the schedule here and make sure it's Sandrine. So if you'll share your screen and introduce yourself.
Perfect. Hi everyone, can you see my screen properly?
Looks good, yeah.
Perfect. So hi, I'm going to be presenting on the Marine NOx Tier III regulation and the impact on the Canadian air quality. So I just want to briefly present the other members who worked on the project. So Mourad Sassi, who was the leader of this project, but also Hani, who just presented earlier, who also actively took part of the project as well. So we're all part of the RECA, so it's the Air Quality Issue Response section in the Meteorological Services of Canada. So before starting, I just want to give a quick introductions on the impact of the air quality and air pollutants. So for instance, NO2 has a direct and indirect impacts on health and the environment. NO2 can have impact on respiratory function, cardiovascular function, fetal growth, and premature deaths as well. We have that NO2 is a precursor to ozone as a secondary pollutant, but also to fine particulate matter. And these two pollutants also have significant impact on health and the environment. And PM2.5 can also impair visibility, which also can have economical impact. And NO2 can also take part in the formation of compounds that can contribute to the acidification and the eutrophication of ecosystems. So then just a quick introduction on the Marine NOx Tier III regulation. So it's a policy that has been established by the International Marine Organization concerning these diesel engines, standards on NOx emission for ships exceeding 130 kilowatts. So it's designed compared to the two other tiers, so Tier 1 and Tier 2 regulations, to reduce NOx emissions and requiring 3.4 grams of NOx per kilowatt hour for slow speed marine propulsion engines, and also less for auxiliary engines. This is applicable only for ships that have been constructed or with their keel laid on or after January 1st of 2016, and for ships that are transiting in the North American emission control area, which is roughly around 200 miles from the US and the Canadian coast, but also including remote islands. So the objective is to assess in this study to see the impact of this policy applied on ships and see the impact on air quality over Canada. To do so, we use the Environment and Climate Change Canada Air Quality Prediction Model, so GEMAC version 2.4.6. So GEMAC is really just the combination of GEM, our model, which is the Global Environmental Multiscale model, in which there's a plugin added to model air quality, so the MAC plugin, which models air quality in the chemistry, which includes, for instance, dry deposition and aerosol chemistry and many more. So the coupling is a one-way coupling. So the material, the GEM model impacting the air quality, but the air quality in return doesn't impact the GEM model, so the Meteo. And at each time step, we have the air quality model is computed. So the model domain is, as you can see on the right, a North American regional grid at 10-kilometer horizontal spatial resolution. And there's also 84 vertical levels. So from the surface all the way up to 1.2 hectopascal. So for the study, all the models inputs are the same. The only one that changes is the marine shipping NOx emission. So let's say the meteorological piloting and also the chemical boundary conditions are the same, but also all the non-marine anthropogenic emissions as well are the same for our scenarios. And they're based on the Canadian air pollutant emission inventory for year 2019, and also from the US National Emission Inventory for the year 2016. So for the marine emissions, they're produced by the Marine Emission Inventory tool, which is developed by the Cross-Sectoral Energy Division of ECCC. So this is not a group that create the marine emissions, but we receive the data from another group within the government. And the platform, so the tool, what it does, it uses the vessel movement data for year 2019 to assess the marine emissions within the Canadian waters. So then these are the three scenarios we've used for the study. So the first one is the baseline. So it's the current compliance to NOx Tier III regulation at the moment, where 1% of ships traveling in the Canadian waters are compliant to the regulation. So there's a total of roughly around 192 total ton of NOx emission for this baseline in the marine emissions. And the second one is the full compliance scenario, in which we suppose 100% of ships traveling in the Canadian waters are NOx Tier III compliant. And then the last one is a partial compliance scenario, where 30% of the emissions are reduced according to the policy. So what we do is prorating the full compliance scenario with the baseline to get this partial scenario. So on the right, you can see the emissions, the spatial distribution of the NOx emissions. So you can see along the shipping routes, mostly near Vancouver, but also through the St. Lawrence Seaway and all the way up to the Great Lakes. And so when looking at the NOx reduction and compared to the baseline, we have that the reductions corresponds to 90% and 65% of NOx emission reduction respectively in the marine sector for these two scenarios. So now let's take a look at the output of the model. So with the scenarios, we basically change the input of the NOx emission. We run the model, and then this is the output of what we've got of the model. So here, this is the NO2 concentration maps. So what you see here is the difference between the baseline and the full compliance scenario. So I'll only be showing the full compliance images because the partial really just have similar images, but just a little weaker signal. So here, what you can see is the difference between the full compliance and the baseline when looking at the annual daily average of the NO2 surface concentration. So what you can notice is a global reduction, a direct reduction led by the fact that the NOx emissions were reduced. And you can see that the signal is mostly localized along the shipping routes, as NO2 is a short-lived pollutant. And you can see that the greatest impact is on the West Coast, so near Vancouver. It reaches up to 65% of reduction in the NO2 concentration. And now when we look at the impact on the ozone, so here this time what you're looking at is the metric for the annual average of the daily maximum, because the ozone is a secondary pollutant form as a photochemical reaction. So it's really depending on the sun conditions. So it's a reaction between a NOx with a volatile organic compound that leads to ozone formation. So here again, we can kind of see an overall global reduction when looking at the difference between the full compliance scenario with the baseline. We can also see that the impact goes deeper in the land because ozone is a more long-lived pollutant than NO2, but with a kind of weaker signal. But this time, which is also interesting to notice, is that near Vancouver, when you look at the right image, we can actually in opposite trend. So we actually have that when all the ships apply to the policy, instead of having a reduction of ozone concentration over Vancouver, there's an increase in ozone concentration. And as Annie specified a little bit earlier during her presentation, this is due to the NOx titration chemical reaction. So this occurs in either VOC limited environment or where we have a lot of NOx emission in very polluted cities. So when there's less NOx, then there's less ozone that's used for the NOx titration reaction. And then inversely, if we reduce NOx, then there's more ozone in the atmosphere. And this time we have that the maximum impact reaches up to 82% on the West Coast again. So now quickly for PM2.5 impact. So we see that the impact for PM2.5 again is a little bit more localized like we had for NO2. And the impact is a bit more modest in the term that when we look at the relative difference, it reaches only 4%, 4.7% in the St. Lawrence River and 4.2% near Vancouver. This is explained by the fact that the NOx can forms into the nitrate component of PM2.5, but it's not a major component of the total PM2.5 mass. And yeah, but although the impact is a bit more modest for the air concentration, PM2.5 is a pollutant that really has a great impact on the health. So even a small impact can still lead to a great impact on the health. So with this difference between the scenarios and the baseline, we've provided Health Canada with our difference into the air pollutant concentration. And with their tool, they ran a study with the air quality benefits assessment tool to see the impact on health, but also a monetized equivalent. So they ran their model with our data. And for the full compliance scenarios, they have that the reduction we see leads to 91 fewer air pollution attributable deaths annually. And this corresponds to, in terms of 2022 Canadian dollars, to $730 million annually. And the main impact is seen over BC, Quebec, and Ontario provinces, which accounts for 87% of the estimated avoided air pollution attributable death. And this is due to the proximity to the shipping routes of these provinces. And then for the postal compliance, it leads to 24 fewer air pollution deaths, and which corresponds to 194 million annually. So just a quick conclusion. So this study, we used 3 scenarios. They're using GEMAG model. So 1% compliance, which is the current compliance to the policy. A partial scenario, which we have 30% of ships or emissions are compliant, and then 100% of the compliance for all ships that respect the NOx Tier III regulation have been ran. The impact, we have a direct impact of reduction of NO2 concentration through NO2 emissions reduction. We have that ozone has also a global reduction, penetrating more inland than for NO2. But we also see an opposite trend in Vancouver due to the NOx titration reaction. For PM2.5, we have that the impact is quite modest in terms of reduction in terms of the concentration, but it still does have an impact on the health. And then again, the health impact of these 3 pollutants leads to 91 fewer air pollution attributable deaths annually, and which corresponds to $730 million annually. So I just want to finish by acknowledging Mathieu Rouleau and also Robin Ridmaster from Health Canada for the air quality benefits assessments with our air quality data. So thank you. I don't know if everyone has any question.
That's great, Sandrine. Thank you. We do have one question. It's what is driving the changes in air quality concentrations deep inland, such as in Alberta? Are there any changes in local emissions there, or is this a consequence of advection all the way from the West Coast?
Yeah, so it's really the advection all the way to deeper inland, because the emissions, as we saw in this figure here, is really just reduced along the shipping routes. So deep in the prairies, there's no really boats that go all the way through there. So it's really, the advection. So for NO2, the impact is more localized along the shipping routes, but for, let's say, ozone and PM2.5 that are more long-lived pollutants, they are indeed advected towards deeper inland. Yeah.
Excellent, thank you. I don't see any other questions. Is there any questions from our presenters for Sandrine? No? Okay, well, thank you very much. We'll move on to our next presentation, which certainly get started.
Okay, you can see my screen, hear me?
Everything sounds good and looks good.
Fantastic, thank you. Well, hello everyone, and bonjour à tous. My name is Paul Bovis, and I'm a meteorologist currently on assignment in the Environmental Emergency Response Section, or EERS, at the Meteorological Service of Canada, or MSC. The focus of this presentation centers on a topic that is of increasing importance within both the scientific community and the public at large. So as forest fires have recently been growing in both frequency and intensity, a quick and flexible emergency response is necessary in order to save lives and mitigate the effects of forest fire smoke to people's health. For over 20 years, the EERS has provided forecast guidance tailored to emergency responders' needs. These cover a wide range of responses, including smoke from forest fires. We are a dedicated multidisciplinary team who operate 24/7. Since 2016, the EERS has been running a suite of automated forest fire smoke dispersion forecasts for not only Canada, but for select regions around the world. My presentation will start by providing a bit of information on the models behind our automated smoke forecasts. I'll then quickly discuss the main features of our automated smoke forecasts, followed by a few initial results of our first major evaluation against observed data. So the EERS uses a variety of Lagrangian trajectory and particle dispersion systems to respond to events at various temporal and spatial scales, be they regional, continental, or global. These include a Lagrangian trajectory system, as well as particle dispersion systems, which can be used from local to global scales, and even incorporate urban geography, such as buildings. Our MLDP system is used for the automated system I'll be covering today. So we use meteorological fields, such as horizontal wind, from Canadian deterministic models as input into our trajectory and dispersion systems. So we use, for responses within Canada, the High Resolution Deterministic Prediction System, or HRDPS. And for international responses, we use the Global Deterministic Prediction System, or GDPS. So let's move on to talk about the main topic for today, which is the Experimental Automated Forest Fire Smoke Guidance, or AutoSIM for short. Before the Fort McMurray fire in May 2016, we only provided on-demand forest fire responses. The guidance products that we provided to clients were only in generic mass units per cubic meter for concentrations of forest fire smoke. This output could not be used by emergency response agencies to drive many of their tactical emergency processes. Now, during and after the Fort McMurray fire of 2016, the EERS continued with on-demand responses, while also developing a suite of automated experimental systems to ease the workload of responders. These automated Lagrangian dispersion systems did provide PM2.5 concentrations in micrograms per cubic meter, which allowed emergency agencies to make detailed decisions based on our products. These automated systems use emission rates of forest fire smoke derived from fire radiative power and total fuel consumption calculations based on hotspots detected from polar orbiting satellites, along with meteorological fields from deterministic prediction systems. So it's important to note that while the MLDP, which is being used for AutoSIM, is not an air quality model in the classical sense, such as Firework, which is available on weather.gc.ca, it is highly configurable, flexible, and fast. It can be run for any location globally, or either on demand or automated. Additionally, because we have established strong partnerships with emergency response agencies over the years at all levels of government, be they national or international, we are already a trusted source for forecast guidance within this community. So we have three main AutoSIM systems, which are run 4 times daily out to 48 hours. The OPS CWFIS 48-hour ingests the previous 48 hours of detected hotspots prior to model runtime. These hotspots are taken from the National Resource Canada's Canadian Wildland Fire Information System, or CWFIS, which uses hotspots detected from NASA's Fire Information for Resource Management System, or FIRMS, but uses algorithms that filter out hotspots not associated with wildfires. CWFIS also makes use of additional polar orbiting satellite platforms to detect hotspots. CWFIS 48-hour is run on 24/7 supported IT infrastructure. Now, PAR CWFIS and PAR FIRMS 24 hours, as the name suggests, make use of CWFIS and FIRMS hotspots, respectively. They only ingest the previous 24 hours of detected hotspots prior to model runtime. They are run on a parallel server with next business day support. So here's an example AutoSIM run from the 15th of May of this year. The output is every hour with higher concentrations of PM2.5 in micrograms per meter cubed in pink, brown, and orange. At this time, the bulk of the activity was in the Northern Prairies and Northeastern BC, centered over Flin Flon, Manitoba, just south of Fort McMurray, southwest of Hay River in Northwest Territories, Fort Liard in Northwest Territories, as well as a big clump in Northeastern BC around Fort Nelson. So this image showcases a sample of AutoSIM's high-resolution output domains within Canada, with output resolutions between 2.5 and 10 kilometers. For our evaluation, we are using an AutoSIM output domain, which is roughly the same geographic area as the HRDPS natural grid, but at a 10-kilometer resolution rather than 2.5 kilometers, which is the resolution of the HRDPS over this domain. So to evaluate the performance of these three systems, we used output from August 6th to 31st, 2023, using one run per system per day. These were compared with hourly PM2.5 observations from the AirNow air quality database. We applied thresholds of 1 microgram per meter cubed for measured and predicted PM2.5 values, and a 50 microgram per meter cubed threshold to focus on high concentrations related to forest fires. As we build out our statistical evaluation, we will be testing higher concentration thresholds as we are primarily interested in evaluating our system's performance during forest fire responses. In this presentation, we will only be using results for the 1 microgram per meter cubed threshold. This is because there were not enough high concentration observations of PM2.5 available in the AirNow database for the range of dates in our study. A full fire season should provide us with enough observational data, particularly considering the last few years of forest fire activity. Also note that the AutoSim systems do not account for anthropogenic emissions, as it is not a dedicated air quality model. Lower values of PM2.5 concentrations in the observational data set could be anthropogenic in nature. However, in our systems, lower values are strictly from forest fires. And so this can lead to issues in interpreting the statistical results at lower thresholds. The application that we built to evaluate our AutoSim systems calculates a wide variety of statistical indicators, and more can be added very easily. For this presentation, I'm just going to be focusing on fractional bias and factor of 2. So for fractional bias, this can be interpreted as a ratio of the mean predicted and observed values, or the ratio between the mean predicted and observed values, sorry. A perfect fractional bias has a value of 0, and fractional biases of 0.67 and minus 0.67 indicate a factor of 2 mean under and over prediction, respectively. Also note that fractional bias can be overly influenced by high observed and or measured values, and also a model can be completely out of phase with measurements and still have a fractional bias approximately equal to 0. So that's something to watch for. Our initial evaluation indicates that the OPS CWFIS 48-hour is over-predicting PM2.5 concentrations by a little over a factor of 2. PAR firms and PAR CWFIS 48-hour are over-predicting PM2.5 concentrations below a factor of 2, with PAR CWFIS performing slightly better, possibly due to algorithms which filter out non-wildfire hotspots. However, their increasing fractional biases over time could be indicating that predicted and measured and observed values are becoming increasingly out of phase. And this is something we're going to have to look into this summer. Again, this is just a very preliminary, these are just preliminary results. We still have a long way to go. So for factor of 2, you can simply think of that as the percentage of the predicted to observed ratios, which have values between 0.5 and 2. A perfect model will have a factor of 2 equal to 100%, and it's a robust indicator as it is not overly influenced by outliers. So our initial evaluation indicates that the OPS CWFIS 48-hour actually has the highest percentage of predicted to observed ratios between 0.5 and 2, even though it has the lowest fractional bias of the 3 systems. This could mean that it has quite a few values within a factor of 2 when compared to the observations, but also many high values as well. And this can skew the fractional bias to even more negative numbers. Up to T+36, PAR CWFIS 24-hour also performs well. So I just got a couple more slides. There's 5 main limitations of MLDP AutoSim. The first is that the plume injection height is fixed at 200 meters. So even though many large forest fires have plume heights much higher than that. Second, the release start time of all hotspots is the same, even though the hotspots are detected at up to 48 hours prior to runtime. Third, the emissions rates are fixed and constant for each hotspot over time. And it does not account for the growth and spread of forest fires over time. There's also a risk of counting the same hotspot more than once with increasing hotspot ingestion time. And so over the summer, we have 4 main ambitions. We would like to rerun this analysis with a full fire season's worth of data. We'd like to evaluate our systems using a variety of PM 2.5 concentration thresholds, the values of which will be drawn from regulations and the established literature. We'd like to further evaluate how hotspot ingestion durations affect system performance. And finally, we'd like to explore more robust evaluation methodologies as established in the literature. So I'd like to thank you for your time. I'd also like to thank my co-authors, Alain Mello, as well as Philippe Barniot, also of the EERS. And I'm ready to take any questions. Thank you.
That was great, Paul. Thank you very much. I'm just checking to see if we have any questions. Not right now, but I do have a couple myself. It's kind of a field I'm very interested in. I do a lot of work with satellite meteorology, so it's kind of interesting to see some of that use there. But one of my questions is I used to be a fire weather forecaster as well for the province of Manitoba. And one thing I've wondered with these smoke models is, do they take in any sort of fire hazard information? Like, do they look at any of the Canadian wildfire danger rating system indices to see if, in fact, there is like that there will be burning that day, like the fire weather conditions support it, or is it just kind of they see a hot spot and if they'll burn the fire and produce particulate matter? So I'm just wondering, is that taken into account?
Not for our models. I can't speak for Firework, which is the dedicated air quality model for forest fires. We keep our systems very simple because we're first and foremost an emergency response agency. So literally we have 90 minutes from the time the request comes in to the time the email goes out with the product. So we need systems that run very, very quickly. And as I sort of pointed out, there are a number of limitations to that due to our response time as well as computing resources. But yeah, I mean, these are things we might look at going forward, but a good question there.
Okay, yeah, and I have a second question too,
Sure.
but there's one that just popped up here in chat, so I'll read that one first.
Okay.
Regarding observational data for evaluating the system, have you considered using small sensor data such as like purple air, and it says such as those on aqmap.ca? These monitors work well when corrected and also cover many wildfire impacted areas in which there is no regulatory monitoring.
We haven't yet. I've just been using stations that are within the AirNow database, and that's kind of like a North American database. But prior to this, I was doing some evaluations of Chilean forest fires. And Chile actually has an excellent air quality network, which is good because their forest fires have been extremely bad as of late. So we can, the application that we do have does have that ability to use external data sets besides just the AirNow database. So we're making it as flexible as we can.
Sounds good. I'll ask my other question to you later. We'll have to continue on so that we don't run out of time. Thank you very much. And then, so just go on to our last presentation here. It is, sorry again, it's Gianina. Is that correct? Sorry.
Yeah,
if I
Gianina.
butchered that. Okay, perfect. All right, introduce yourself. Well, first share your screen and introduce yourself, and we'll get started.
Okay, can you see my screen?
Yes, we can see you, and we can see it and hear it. Thank you.
Okay, great. So my name is Gianina Giacosa, and I'm a PhD candidate at Dalhousie University. My supervisor is Rachel Chang. So what I'm going to present now is my partial results from my thesis. So the presentation is entitled Fog Droplets and Aerosols Interactions During Marine Fog. So I'm going to start with a brief introduction about fog and visibility, then talk about my goals and the field campaign that I went to collect the data and some preliminary results and some future work. So fog is defined as visibility below 1 kilometer according to the World Meteorological Organization, and it mainly consists on suspended water droplets or ice crystals in the lower atmosphere. And typically, the human visual range would be 300 kilometers. However, in the presence of fog of aerosols, this visibility decreases. The extreme case would be the fog where visibility drops to below 1 kilometer. And we care about that because this poor visibility affects negatively transport operations like aircraft or ships or even road traffic. And fog predictability is still among the poorest in meteorology, and that's mainly because the processes involved in fog formation and dissipation includes processes that goes from the synoptic scale up to the microphysical scale. So how all these processes interact among each other is still not very well understood. So trying to better understand all the processes involved in fog formation is that the FATIMA project, the fog and turbulence interactions in the marine atmosphere, started a couple of years ago. It consists on some universities and institutions from the US and in collaboration also with Canadian institutes. And so there are different groups working on the different scales involved in fog formation and dissipation. And in particularly, I'm interested in the microphysical scale of fog. So that involves fog droplets and aerosols. And so my goal is to understand how aerosol size distribution change during the fog life cycle. So what I'm starting to do is basically comparing how aerosols size distribution change before, during, and after a fog event, and also comparing different fog events. So to trying to understand if the aerosols distribution are different when fog occurs on different places and how it relates with droplet formation. So the campaign that we went first was in the North Atlantic Ocean. It included the Grand Banks and Sable Island. So it happened almost 2 years ago during July. And here is the trip that the ship did. It started from Halifax, then stayed around 2 weeks on the Grand Banks, and then went back to Sable Island and stayed around 2 weeks there. Yeah, just hoping to get marine fog. So the way that I started analyzing the fog cases was just using fog definition of being visibility below 1 kilometer, and the visibility data that I used was from a present weather detector, FD70P, from University of Notre Dame. And then to define fog events, I used like the criteria that fog should last at least 2 hours as minimum. And after identifying the fog events, I look at the aerosol size distribution during those events using scanning mobility particle sizer and SMPS, which measures aerosols diameter between 0.010 microns to 0.5 microns, and it scans every 5 minutes. And the air that I sampled was dry aerosols, as we had a silica dryer aboard the ship, and we were replacing the silica bits frequently to ensure that the relative humidity was below 30%, so that way we were measuring dry aerosols and not dehydrated aerosols. So just an overview of the data for the whole campaign. We can see here in the x-axis the visibility, and then the y-axis is aerosol concentration. The orange points are all the measurements that happen in Sable Island, and the blue ones are on the Grand Banks. So we can see how lower visibilities here happen most frequently on the Sable Island region, and they were also associated to higher aerosols concentration. On the other side, the ground banks had a more like dispersed aerosol concentration that ranged, but the concentration of aerosols was still lower than in Sable Island. Yeah, and then I'm going to just talk about two case studies, one on ground banks and the other on Sable Island. So one in the ground banks that happened on July 11 lasted for around 6 hours. So here we have aerosol size distribution on the x-axis, aerosol diameter on the x-axis and aerosol concentration on the y-axis. The blue line represents the average on aerosol concentration from 1 to 3 hours before fog. The orange line is the average on the aerosol concentration on the 6 hours that the fog lasted. And the green one is aerosol concentration from half an hour to up to 2 hours after the fog dissipated. The shaded area represents one standard deviation. So we can see that for most of the aerosol sizes, the concentration of the aerosol decreased from pre-fog conditions to dissipation conditions, except for aerosols larger than 2 nanometers here, that we can see that there is a slightly increase of aerosol concentration during fog and after the fog dissipated. But for this icon mode here of aerosols, the concentration decreased. And if we look at the aerosols size distribution during the fog event, so this figure here, it's just all the fog period split it into the initiation stage of fog in red, mature stage in purple, and the dissipation stage in brown. So yeah, again, we see the same, that from the beginning of the fog and up to the dissipation stage, the aerosol concentration in this icon mode here decreased. However, in the accumulation mode, the aerosol concentration didn't change that much in any of the fog stages. If we look at an event in Sable Island, this event lasted for 36 hours. So again, we have the aerosol distribution here. And the same, we can observe that aerosol's concentration decreased from pre-fog conditions to post-fog conditions. And one difference in this case is that aerosols before fog are not bimodal. The aerosol distribution in this case is unimodal, particularly on average on the whole event. It's just unimodal in comparison to the previous event that was bimodal. And if we look at the aerosol size distribution during the fog event, we see that at the beginning of the event, the aerosols had a unimodal distribution, but by the end of the event, throughout the dissipation, it's not only the concentration of aerosol decreased, but also it turned into a bimodal distribution. And when we look at the droplet size distribution for each of those events, in this case, I use a fog droplet monitor from Naval Postgraduate School. So for July 11, here we have, again, in the y-axis, we have concentration of droplets in this case, and the x-axis shows droplets diameter. And we can see that there is a bimodal distribution in this case, and the peaks, like the location of the peaks don't change significantly throughout the different stages of the fog life cycle. The small peak here remains between 3 to 5 nanometers, and the larger peak here, it's around 26, 28 micrometers. However, the concentration of the droplets associated to this small peak here start to decrease from the beginning of the fog up to the dissipation stage of fog. And the same thing happens here. The concentration of the larger droplets decrease from the beginning of the event up to the dissipation stage of fog. And when we look at the larger events that happen in Sable Island, again, we observed that the droplets were characterized by basically two bimodal distribution. However, even though this event lasted for almost 40 hours, this peak still, like the small peak, was kind of at the same size, and the concentrations didn't change that much. However, the larger droplets, the peak on the larger droplets, the concentration tend to decrease by the end of the event. And in this case, in the small case, they slightly increase by the end of the event.
2 minutes.
Yeah, thank you. So to wrap up, some general conclusions about the two events is that in the Grand Banks, the events that we observed were all like short events. They lasted less than 12 hours, while in Sable Island, the events lasted more than 24 hours. On the Grand Banks, the aerosol distribution was mainly bimodal, and in Sable Island, this distribution was unimodal at the beginning, and then it transitioned to a bimodal distribution. We observed lower concentrations of aerosols on the Grand Banks and higher in Sable Island. And this might be related to the source of the aerosols. When I look at the trajectory of their masses 24 hours before formation using the high split model, it seems that the air mass that leads to fog formation on the Grand Banks, it's mainly originated in the Grand Banks area. So it's the aerosols there are most influenced by sea salt particles. And on the other hand, the air mass that leads to fog formation on Sable Island seems to be influenced by continental emissions from the US coast. So a general conclusion is that for all the events is that aerosol concentration decreased during fog in comparison to pre-fog conditions, and also that the peaks that were observed when looking at the droplet size distributions, they seem to be fairly constant throughout the fog events and throughout the fog life cycle, with a small peak between 3 to 5 microns and a larger peak from 24 to 28 microns. And some future work that I'm kind of starting now is trying to incorporate chemistry, aerosol chemistry, and trying to understand if the unimodal or the bimodal distributions, how chemical composition may be affecting these distributions, and also relate those to droplet formation. So thank you.
Thank you very much. Let's see, we have time for some questions, but does anyone have any questions for Gianina? We don't see any in the chat so far, the Q&A. Let's give it a minute here just to see if we have any questions that trickle in. Yeah, it doesn't look like that, but does anyone else have any questions for any of the other presenters we had during this session? And it looks like it's all silent. The fun part about virtual Congress is you get to try and see if there's any questions that come in late, I guess, or the interaction's all silent all the time, or parts of it anyways. I would like to thank everybody for their talks in the session. It was very interesting. I personally learned a lot. Some of this stuff is out of my realm, but it's just interesting to see kind of the different science that's happening in our country with respect to this. So there's lots of missions talks and air quality stuff here today, which is all super important. And I was really impressed with what I saw. So so with that, we'll conclude the session for now. But just a reminder, this is part one of three parts session. So the next session will start at 2:05 p.m. Eastern Daylight Time. So hopefully we'll see you then. but for now, see you in about, I guess it'll be 15 minutes or so. Thanks. Is Darby.